So just like with energy, there's a conservation principle for momentum. So let's talk about the one we know first and see if that can help us set up this new conservation principle. So when is energy conserved? Well, again, if you look at our energy balance equation, initial kinetic, initial potential, that's the initial energy. Final kinetic, final potential, that's the final mechanical energy. So those two things are going to be the same when the work done by non-conservative forces is zero. So energy is conserved, meaning that the initial is equal to the final when there is no work done by non-conservative forces. So if we think about how to calculate the work done by non-conservative forces, well, for any non-conservative force, whether it's constant or not, we can write it in this form. And we said there's three different ways that you can make this term be zero. You can have no non-conservative forces. Obviously, that would make the work done by non-conservative forces zero. You can have no displacement. So you do have non-conservative forces, but there is no displacement of your object. Again, then the work done by non-conservative forces would be zero. Or you can have a situation where, because of this dot product, the non-conservative forces are perpendicular to the displacement. So all three of those are options. There's three different ways for how the work done by non-conservative forces can be zero, and therefore energy will be conserved. So when is momentum conserved? Well, again, let's think for a second about the momentum impulse theorem. And you notice it says that the change in momentum is equal to the net impulse. Well, one way to say momentum is conserved is to say that it doesn't change, so that means if the change in momentum is zero, then the net impulse has to be zero. So one way to think about when momentum is conserved is to say that the net impulse acting on our system is equal to zero. So what does that mean? Well, we said we calculate the net impulse in this way. But again, the thing that's interesting about this is, unlike in the previous version where there were three ways to make the work done by non-conservative forces equal to zero, there's only one way to make this term zero, and that's to make the net force be zero, right? dt can't be zero, or else you're saying time doesn't change at all, and you can't stop time. And again, there's no dot product here. So the only way the impulse can be zero is if the net force is zero. So here's sort of our requirement for momentum to be conserved. Well, if we think about Newton's third law, we can break the net force up into two types of forces. So one is internal forces. So internal forces are defined to be all the forces that stuff within our system exerts on other stuff within the system. And then external forces is all the forces that stuff outside the system exert on stuff inside the system. So inside the system is the on in both of these terms, but we're changing the by. So internal forces, it's going to be forces on our system, by our system. And external forces is going to be forces on our system, by stuff not in the system. Well, what Newton's third law tells us is, because for every force there's a Newton's third law pair, that as long as both things are inside our system, that when you sum this up, this is always going to be zero. So the sum of all the internal forces within your system is always going to be zero because of Newton's third law. Which leaves us with this term. So that tells us that momentum is conserved when the vector sum of the external forces acting on the system is zero. So that's a situation where momentum is going to be conserved. Another way to think about this, again, we can come to the same conclusion by thinking about Newton's second law. So we said Newton's version of Newton's second law tells us that the net force is equal to the time rate of change of momentum. And again, if you want momentum to be conserved, that's another way of saying momentum is constant. And for momentum to be constant, that means that this dp dt term's got to be zero, so it can't change. Well, clearly if you make this term equal to zero, then that tells you that the net force has to be zero. And again, we can break up that net force into two pieces. Some of the internal forces plus some of the external forces. And again, from Newton's third law, we know that the sum of the internal forces is going to be 0. And so we're left with the same conclusion. Momentum is conserved when the vector sum of the external forces acting on the system is 0. So what does this mean? Well, or where are we going to use this is probably the better way. So obviously, anytime that the net external force is 0, momentum will be conserved. The most obvious situation in which we will use this is during collisions. So for a collision, what happens is you've got a brief, intense interaction between objects, and the objects that are interacting are all going to be considered part of the system. So the brief means it's going to happen for a very short period of time. We're going to take advantage of that in a minute. And intense tells us that the forces between our interacting objects are going to be much larger than any external forces acting on the objects. And we'll see there are going to be situations where we take advantage of this. So what this means, though, is that during a collision, because they're brief and because they're intense, those interactions are brief and intense, the effect of the external forces acting on the system is basically negligible. So momentum is always conserved within a collision. So this tells us that the final moment, or the initial momentum of our system, which is just going to be the sum of all the momentum of the individual pieces, has got to be equal to the final momentum of our system, which is just the sum of all the final momentum of the pieces. So again, momentum is always conserved during a collision. So let's say we've got a situation where we've got two masses and they're sliding towards each other. Mass 1's got an initial velocity, mass 2's got an initial velocity. Again, I can think about the free body diagram, and initially as they slide towards each other, the only thing that's acting on my system here is external forces. I got a normal that points up on mass 1, a weight that pulls down, a normal that points up on mass 2, a weight that pulls down. Again, because my objects aren't accelerating up or down, these forces have got to cancel out. So here's a situation where there's no net external force acting on the system. And then as these things slide together, what I end up with is now they come into contact. And as they come into contact, we said these four original forces were external, right? Normal on mass 2 from the surface. Gravitational force on mass 2 from the Earth. Normal on mass 1 from the surface. Gravitational force on mass 1 from the Earth. But once they're in contact during the collision, there's this new pair of forces, and you notice that they're both applied forces. This is the applied force on 1 by 2. This is the applied force on 2 by 1. And so Newton's third law says that, hey, when you add these two things together, they got to cancel each other out, because this is a Newton's third law pair. Same type of force, equal in magnitude, opposite in direction. We've switched who's causing the force and who's feeling the force. So this is our internal force, right? Both pieces here are part of the system, mass 1 and mass 2. These are all external forces. One piece is in the system, mass 2 or mass 1, but the other thing interacting in this force, in each of these four forces, is not in the system. So the surface is not part of our system, the Earth is not part of our system. So these are all external forces, but the external forces cancel out, and the internal forces we know are going to cancel out. So again, momentum is going to be conserved during this collision. And so that leaves us with a situation where they'll come in, they'll collide, and then they'll go away from each other. And again, it may be that their speeds are most likely different when they leave based on the collision. There are situations where both of them will bounce back. There are situations where one of them will continue going in the same direction, the other one, so they'll both be going instead of going in opposite directions, they'll both be going in the same direction after collision. Right? All of this is stuff that I can change by changing what the masses are and what their initial speeds are. But the important thing is that momentum is always conserved during a collision. Always, always, always. And if I've got two pieces colliding, then basically what I'm going to do is I'm going to have the total initial momentum of my system is right here. Mass 1 plus V1 initial plus mass 2 plus V2 initial. That's the total initial momentum of my system. That's got to equal mass 1 times V1 final plus mass 2 times V2 final. That's the total final momentum of my system. And again, these are vector problems. This is a vector equation. So there's really a x component equation for this and a y component equation for this. So how we distinguish between types of collisions is really thinking about what's going on with the energy. So there's sort of four types of collisions that we'll typically talk about. So starting with totally inelastic. And so how do you know it's totally inelastic? Well, basically for a totally inelastic collision, your objects stick together. You lose as much energy as you possibly can in getting your objects to stick together. So a totally inelastic collision, you've got the maximum amount of energy lost. So the only thing conserved in a totally inelastic collision is momentum. For a partially inelastic collision, well, your objects don't stick together, but you still lose energy. So again, the only thing conserved in a partially inelastic collision is momentum. For an elastic collision, elastic is the special sort of situation where, again, we said, hey, we've got an elastic potential energy. And so what happens is during the collision, your objects basically utilize an elastic potential energy to store the energy during a collision, and then they get all of it back after the collision. So an elastic collision is the one case in which both momentum and energy are conserved. And so how do you know it's an elastic collision? Well, as a general rule, you just have to be told. So I got to tell you the two objects collide via an elastic collision. Well, now we know that we can use both momentum and energy conservation. The other type, or the last type of collision, again, you can think of it as a superelastic collision, which means maybe what I've got is I've got two objects, but there's a spring. So there's something that's bringing additional energy into what's going on. So a superelastic collision is just a name for a collision in which I gain energy. So again, only momentum is conserved in this type of collision because energy, I end up with more at the end than what I had at the beginning. And so maybe I do that because I've got a spring that I'm going to use to add energy. Maybe I do that by basically running a collision in reverse. And the easiest way to think about a collision in reverse is basically to say, well, that's what an explosion is. So if you think about a gun firing, right? A gun fires through basically, instead of two things come towards each other and stick, well, they're initially stuck together and they explode away from each other. So again, that's a situation where momentum is still conserved, because the net external forces acting on everything is very small, or is zero, or is negligible, depending on the type of scenario and the problem. So we can say that momentum is conserved, but there's clearly an addition of energy, right? So before you fire the gun, your system, gun and bullet, has no net kinetic energy. But afterwards, obviously, there's kinetic energy from both pieces because your bullet fires forward at a high speed and your gun recoils backwards. And the gun recoils backwards, again, to make sure that momentum stays conserved. So these are the types of collisions we'll deal with. Again, it's only in this very rare case where anything more than the momentum is conserved. So momentum is always conserved in a collision, but only in the special case of an elastic collision do we conserve anything else. Most collisions we're going to lose energy. There are some ways we'll find actually gain energy. But as a general rule, momentum is always conserved, energy only if we have an elastic collision.